All right. That's actually going to give us an insight for how we're going to now do this in the continuous case. So in the continuous setting, we'll consider this 1D object as, and oftentimes we'll have it have a variable density given by rho sub x. What do I mean by a variable density here? Well, if we imagine this, so what we're going to do is we're going to imagine this mass as being maybe something like an infinitely thin rod. Okay, so the thickness of the rod doesn't matter. We're going to imagine that it's basically an infinitely thin rod living on the x-axis, but what we do have, even though it doesn't have this sort of infinite thinness, is we imagine it as having a variable density. And so I'm trying to represent density here by drawing these dots, where the more compact the dots, the denser the object, and the more spread out the dots, the less dense the object. So you can see that this object does not have a uniform density, and so what we would say is that rho sub x tells us the density at any point x. Okay. Now that we've got that, we can start talking about the mass of this infinitely thin rod. So the first thing we ought to realize is the relationship between mass and density. And we have a formula that I'm not going to worry about deriving that says we define density, or we can call density, oops, we're jumping around there. We define density, or we can call density, the mass of the object, the total mass, divided by the total volume. Now, in the case we're going to do this in 1, 2, and 3D. In 3D, I think we all know what volume is. In 1D, this will just be length. And in 2D, this will be area. And in 3D, then this will be volume. So we'll keep calling it volume because that makes the most sense. But remember that in the 1D case, we make the assumption that this object is infinitely thin. It has just one dimension to it. In the 2D case, we'll be looking at a infinitely thin plate, and it's not until the 3D case where we would have volume as we traditionally represent it. If I were to solve the expression density is equal to mass divided by volume for mass, we get mass is equal to density times volume, or keep in mind here, we're going to think of that as density times length. Okay? So that means that we can think of the mass of this rod as the limit. And here, so we'll fill that limit in just a second. What we're going to do is we're going to take and break this rod up into sub-pieces, as has been done in this video here. Notice it's been broken up into n sub-pieces. So each one of these has a small unit of volume. Careful, when I say volume here, what I'm referring to is the length of that piece, because we're in 1D, and the volumetric equivalent in 1D is length. So we've got this little interval of length, right here, and we're going to multiply that by the density of that chopped up segment. So remember we said that we're going to think of mass as the density times that little increment of appropriate volume, whether that's length, area, or volume. So we're going to take from each one of these points, or from each one of these segments that we've broken this rod up into, a representative x-coordinate, call it x of that x of k star, and then we're going to put that representative x-coordinate into our density function to give us the density at that point, and then we'll say that approximately the mass of this entire tiny segment is just the density of that segment evaluated at that one point times the length of that one point. So let's just say that we're going to take some xk, and we're going to, xk star is usually what we use for this, and we're going to plug that x of k into our density function here, and that's going to give us the density, what we're going to use is the representative density over that entire interval. And then we're going to multiply that by delta x of k, where x of k is the width of this little interval right here. Then what we need to do is we need to sum these up from n equals, from k equals 1 to k equals n. So from k equals 1 to n. Now, folks, I have an error here because I put equals, and this is just approximately. And in fact, though, we'll say that the mass of the rod is the limit. And if we assume that we've cut this up into equal intervals of equal size, this will be the limit as delta x approaches 0 of the sum from k equals 1 to n, rho sub x of k star delta x of k. But careful here, we said that we're going to assume they all have the same width just for simplicity of giving this definition, so we'll put just delta x there. But this is just the definition of the integral from x equals a to x equals b. Notice that we would get, in this case, delta x would be b minus a over n, where a and b are the two endpoints. So this is just the integral from x equals a to b of rho sub x dx. And here's how I want you to think about this, folks. Here we have a density evaluated at some point along this rod, and we're multiplying it by an infinitely small unit of length. So we're taking density times length, which is the same thing as density times whatever the volumetric notion of length is in the dimension that we're in. So in this case, length is what we're thinking of as volume here. So we're taking density times volume, and that gives us the mass at that one point along the rod in limit. And then if I add up the mass at all points along the rod between x equals a and x equals b, that will give me the mass of that rod there. Okay. That's actually not anything new. We've discussed this before, even though we didn't do the derivation of it. We've discussed the idea that we can think of mass as being an integral over a density function. And so there's nothing new there. But what we want to do now is we notice that in the work that we did up above here, we need the total mass of the system. Well, now we've got a integral that gives us the total mass of the system. It'll be this integral right here that we've developed. But we also need the total moment of the system. Okay? And in this case, we're going to use what we saw up above here as our guide, where we took a point mass and multiplied it by its x-coordinate, and then added to that a point mass multiplied by its x-coordinate. And we could do that discretely as often as we wish. And in terms of a limit, we would say then that the total moment, and I'm going to do this in a different color here so I can draw on it, that the total moment in this case would be the integral from a to b of x rho sub x dx. So the question should be, where does that x factor come from? And without going into too detailed of an explanation, that x factor comes from just what we saw up above here when we computed the total moment. We took each point mass and multiplied it by its x-coordinate. And so here you can see for each point along this rod, as x goes from a to b, let's go ahead and put x equals to x equals. As x takes on the values between a and b, we take that x-coordinate, multiply it by density times a infinitely small unit of length. But this is a small unit of mass. So let's say it's the mass. And I'm putting mass in quotes there because it's point-wise. But mass at x. So we're taking the mass at point x, multiplying it by x, and that's doing the exact same thing that this sum was doing up above here, where we're taking mass times an x-coordinate, mass times an x-coordinate. And so that gives us the total moment. Okay. The last thing I want to say about that is that we could think of this in this image here, is we could think of there as maybe here is where x is equal to 0. And then here, this is our arbitrarily thin rod. Now, we only drew boxes there to fit in the usual idea of having kind of a chopped up interval, but it's kind of hard to just look at the divisions like this. So that's why the author's drawn boxes here. So what we have here is this rod, and the rod starts at x equals a, and the rod stops at x equals b. And the way I want you to think about it is when we're computing the total moment, we pick an x-coordinate. Say we take this x of k right here. We've got this x-coordinate. We've got this representative x of k star. And what we're going to do is we're going to take this x of k, first of all, evaluate the density at that point, and multiply it by a small unit of length. That gives us the mass of the kth box, which is, again, that rho sub x of k star delta x of k. That gives us the mass of the kth box, but then what we want to do is multiply it by its lever arm there, which would just be x of k. That's the distance the x-coordinate is from the x-axis. And so we think of there as being sort of a lever arm right here, and this mass is applying a force to that lever arm, and that gives us that little x times or that little mass times its x-coordinate, just like what we saw up here. Now, the only thing I want to say is that I've a little bit misled you here, in that here we started this off by thinking about it as torque, and while that's true, this mass, this rod, just sits on the x-axis here, so there really isn't a torque because it's a stationary mass, and that's why we use the word moment as opposed to torque. But I think that until you really get into the nitty-gritty details of this, if you would rather think about this total moment as the torque that's generated by this entire rod, you could go ahead and do so. So you're going to take basically the torque and then divide it by the mass of the rod to come up with your center of mass. So let's just say that one more time. To find the center of mass, we're going to take the total moment and divide it by the total mass. And so in our case here, that will be the integral from x equals a to x equals b of x rho sub x dx. And we're going to divide that by the total mass, which is the integral from a to b, say x equals a to x equals b, of just rho sub x dx. And notice you get to be very careful in reading these formulas, folks. This has an x rho sub x, this just has an rho sub x. But this will be our formula for computing the center of mass of a one-dimensional object. And so in the next video, we will recap that like I did right here, and then we'll go ahead and actually find the mass of a rod where we've got variable density. So folks, if you ever get stuck on the idea of center of mass, I think returning to this discrete case is the most important thing to do, to see where we get the idea of total moment divided by total mass, and then to see how we can actually develop an integral that computes the mass by just taking pointwise density and multiplying by an arbitrarily small unit of length, adding that up over the entire region gives us the total mass, and then we get our notion of the total moment from this expression right here, where each point mass was being multiplied by its x-coordinate, and that's exactly what we see happening right here. We're taking a point mass, which is the rho sub x d sub x, and multiplying it by its x-coordinate to get that notion of sort of like torque for this entire system. All right, folks, in the next video, we'll pick that up, and I'll see you there.